Welcome to week 6. This week we're moving on from three-dimensional motion to talking about non-inertial reference frames and rotational motion. There is a lot to cover when it comes to these topics. This covers several chapters in your book. Now, in deciding what I wanted to talk about in this first week, I was thinking about what is going to be most relevant to your classrooms. And I immediately thought of torque and rotational kinematics and rotational dynamics, looking at the motion of a rigid body as it rotates. Well, as it turns out, torque is barely touched upon in your textbook. And rotational kinematics is not in it. There's a lot more emphasis on angular momentum and rotational energy. And I think this is because physicists spend most of their time thinking about atomic systems or molecular systems or galactic systems. Physicists don't actually work on the scale that we look at on an everyday level that much, but at the same time it is really important to our students because civil engineers and various other sorts of engineers all really do care about torque. So I just thought that was an interesting thing to think about because I'm always thinking about, okay, why is this part of the core physics curriculum? We're all teaching what we're supposed to teach, but why is that what we're supposed to teach? All that to say that because torque is what's important in your classes, one of the things that's important, I want to start there. We will get to looking at non-inertial reference frames. So we'll look at the Coriolis effect and the centrifugal forces. But you know what, if there's something else that you feel very strongly you want us to cover, please tell me in the problem solving discussion. I will read what you want and I'll do my best to customize. Okay, so let's get started. So when we're doing everything in translational motion, basically we've been using for the most part F equals ma to do a lot of stuff. Well, in our analogy to rotational motion, that takes us to torque, which is moment of inertia times angular acceleration. Now, torque is R cross F. That is a cross product. And I'd be interested to hear how you do torque with your students. Now, I'm guessing it's more like something RF sine theta is the form you use. Now, here's what we're going to spend most of our time today talking about is moment of inertia. So, how do you teach moment of inertia to your students? I'm guessing if you're doing on-level physics or even honors physics, you probably just give them formulas for moment of inertia for various objects. Do you do the parallel axis theorem with your students? If you're teaching APC, you could have them actually calculate moment of inertia from various objects. And please share if you do that. We are actually going to spend most of our day today calculating moment of inertia. So we have our integral to calculate moment of inertia. Okay, what does this mean? Why do we care? So if we just have a point particle, say this is our rotational axis and we have some particle over here, and it's a distance r away, it has mass m, the moment of inertia for that would just be mr squared. Well, why is that our moment of inertia? Well, if we go back to this equation up here, well, moment of inertia is the resistance of an object to having angular acceleration. It's the resistance of an object to changing its rotational motion. Equivalent to mass, which is the resistance of an object to translational motion. Well, it kind of makes sense that this depends on how far out the object is from the axis of rotation. It's similar to torque. The further something is away from the axis here, the more that mass is able to resist changes in motion. So it's mr squared. What this integral over here does is it allows us to calculate the moment of inertia for any assortment of masses, any shape of mass. So it's just a sum. If you say you had multiple objects, like 3 masses here, you would have mr1 squared plus m2r squared plus m3r squared. I'm forgetting my subscripts a lot. But this integral is more general. It lets us look at every little bit of mass at some distance away. So you will be in the end, you do need to integrate over something in position, not over mass. So you're looking at some infinitesimal portion of mass at the position r. And you're going to add all that up to get your moment of inertia. Now, before we dig into doing these calculations, let's think about moment of inertia more conceptually. Okay, so what I'm going to do is I'm going to give you 3 pairs of objects, and I want you to tell me which one has a bigger moment of inertia. So I'll go ahead and draw those. Okay, so this first pair of objects is 2 rods, but one, the axis of rotation is at the end, and the other one, the axis of rotation is near the center. But they are the same mass and the same length. Pair 2, we're going to say these 2 are the same mass. They're the same shape of object, but in the one on the left, the axis of rotation is on the skinny end, and the one on the right, the axis of rotation is in the fat end. And in pair 3, the dashed lines are where the object's filled in. So this is more like a hoop, a little bit oblong, and the one on the right, it's kind of an oblong wheel. And just say in every pair that the mass is the same. And we'll say that the radius of these 2 objects is the same, and the overall dimensions of the objects in pair 2 are the same. So take a minute and think about in which case the moment of inertia is bigger. Okay, so mass contributes more to moment of inertia the farther away it is from the axis of rotation. So in the first pair, the first object has a bigger moment of inertia because more of its mass is further away from the axis of rotation. In pair 2, the first object again has more moment of inertia because more of the mass over here is further away from the axis, whereas most of the mass is over here near the axis over here. In the third case, because more of the mass it's all concentrated in the outside of the hoop rather than distributed all over the hoop, the first object in the pair has more moment of inertia, or greater moment of inertia. Okay, do you do any conceptual activities on this topic with your students? If you like that activity we did from the University of Washington tutorials, they have, it's a book that you can buy, and they have those they run mechanics through even waves, and so they do have one on torque as well. Okay, let's do some calculations. So let's start with something that's linear. So if you're looking in your book for this topic, they actually do derive many of the common moments of inertia, but I feel like the explanation is a little bit lacking. But I thought I would do a little bit of variations on that. So let's start with something that's linear. So we have a rod of length L, but I'm going to put the axis of rotation a quarter of the way into the rod. So x equals 0 is going to be right here. This end of the rod is x equals minus L over 4. And this end of the rod is x equals L over 4. And the total mass of the rod is m. Here's our formula we're working with. Well, what exactly is this dm? How can we work with this? We want to end up in coordinates of x because that's what we can integrate over. To cover the entire rod, we need to go from one end of the rod to the other. So instead of r, we're going to go to x. And now we need to get dm in terms of x as well. Well, if something's a line, instead of density being a mass over volume, in a line we can say that density equals mass over a length. And because it works that way, we can actually say that dm equals rho dx. Here's a good way of thinking about it. So dm is the infinitesimal mass at every little point. We're chopping up this bar into infinitesimal mass pieces. So the mass of each little piece of bar is the line density, which is m over L, multiplied times the infinitesimal length of this little bit right here. So that's dx. So dm is rho dx. And we just calculate rho over here. So that's our dm. So we have x squared. Now our rod goes from minus L over 4 to L over 4. Okay, now we have an integral we can do. So we get x cubed over 3. Oops, it should be 3L over 4. Okay, so what does this give us? Well, we have m over 3L that we can just pull out. Okay, so I can reduce this L to L squared. In simplifying fractions, I end up at, alright, there's our moment of inertia, 7/48 ml squared. So, moment of inertia should always have units of mass times the length squared. It's this fraction that you get out in front of it that you don't know. So you can go through this whole process to find the formulas that you'll find in any textbook. A rod rotating about its end or about its center, but I just picked a different point for fun. Now, I'm going to ask you to do another variation on the classics. Okay, here's what I want you to do. So we have a rod here rotating about its end. Its length L. I have not given you its total mass. What I've given you is a density. Now this is a special rod where the density is proportional to x. So the farther away from the end of the rod you get, the denser it gets. Okay, go ahead and see if you can figure out how to calculate this moment of inertia. We'll start with our usual, so it's still the case that dm equals rho dx, but now rho is a function, so that becomes kx dx. Now this r still becomes x, and we have x squared kx dx. And now x runs from 0 to L. So if we do this integral, we get, alright, so there's our moment of inertia. Now let's look at an example that's cylindrical rather than linear. So there's 3 major forms of coordinate systems. The Cartesian, the standard one, cylindrical, which is very similar to polar, and spherical. Now when we're doing rotational motion, we want to stick to linear and cylindrical because it's always going to be rotating about an axis. And when you're doing spherical, well then you would be rotating in who knows what direction about a point. So that would be a more complicated problem. And we're just talking about rotating about a single axis right now. Okay, so let's do our example. So here I have a solid disk, and your standard solid disk you can find in your tables that you probably have in your textbooks that you teach the classes with. And well, there's a table in your textbook for this class as well. But here I've made a variation on the problem where density is proportional to r squared, so the farther out from the center you get, the denser the object gets. But even more extreme than the example you did a minute ago. We've got our standard formula. Now we're using cylindrical coordinates now, so we are going to leave this as r. We need to integrate over r though. R is going to go from 0 to big R. So dm needs to be in terms of r. So how can we do that? Well, because we're integrating over little r, that means we're integrating little bitty circles all the way around. So basically, the density in this case is for a surface area. So instead of density being mass over a length, now it's the mass over an area. So to find a little infinitesimal area of mass, we need to multiply the density times the little infinitesimal area. So area in this case, we're looking for the area of this thing right here, this little loop. So we know how far it is all the way around because that's the circumference. So that's one dimension of it. And the other dimension, that's just how thick it is, and its thickness is dr. So it's 2 pi r dr. Okay, so that means that dm can be written this way. Let me know if that makes sense. It's a little bit tricky to think about. I find that reasoning in spherical and cylindrical coordinates can be challenging. Okay, so now dm, if we work that all out, equals, because it's kr squared for us. Oh, and I should point out, this rho equals m over a only when you're talking about something that's either uniform density or you're looking at an infinitesimal bit. Okay, so looking at our dm again, now we have kr squared 2 pi r dr. Alright, so we can plug that into our equation now. We need to integrate from 0 to big R, like I said before. Alright, we do this integral Okay, there's our moment of inertia. Now I'm going to give you an example to do. Okay, so now I've given you a solid disk, radius r, but now the density is k over r. Here's something that's be fun to think about. What are the units of k? I haven't actually worked this out, I'm just thinking about it now. Well, let's figure it out now that I'm thinking about it. Okay, random aside. Okay, so if mass equals rho times an area, then rho has units of kilograms per meter squared. And k is what we're wondering the units of, and r has units of meters. Okay, and that means that k has units of kilograms over meters. Okay, mystery solved. So find the moment of inertia for this disk with this density. Alright, our trusty formula. So what's dm in this case? Well, we just figured that out before. But now our rho of r is k over r. Oh, that means these r's cancel out. So I becomes... Alright, so that's our moment of inertia for this disk. Now the last example we're going to look at is for a spherical shell. Now, as I just said, using cylindrical coordinates and linear coordinates are pretty natural for rotation, but for spheres, it can be a little bit harder to think about. So we're going to do one example together where I will ask you to do various parts of it, but I'll guide you the whole way. I think this is the best 3D drawing I've ever drawn for this class. Okay, so we're talking a spherical shell, so all the mass is on the surface. So again, we get in a situation where mass equals rho times A, or rho equals mass over the surface area. Well, the surface area for a sphere is 4 pi r squared. Here I've got my capital R because that's the radius of the full circle. Now, we're going to say that it's rotating about the z-axis. Okay, so basically what we're going to be doing is adding up the moment of inertia of all these little hoops going around. Add them all up. So, at z equals 0, there's a hoop. At z equals 1, there's a hoop. But because this is a spherical surface, working in z is probably not going to be the easiest coordinate system to work in. So, here's my question for you. So, I want you to think about what the moment of inertia would be for just a single hoop if you knew its mass and you know its radius. Its mass and its radius. What would be the moment of inertia for that hoop? Remember, all the mass is on the edge of the hoop. There's no mass in the middle. Think about that for a minute. No calculation necessary. Okay, well, the moment of inertia for that is just mr squared because all of the mass is r away from the axis of rotation. That means if we're doing the moment of inertia like the infinitesimal moment of inertia for an individual hoop, it's r squared dm. So the radius of the little hoops is varying, right? That's a straight line in here. And each one of those hoops has its own little infinitesimal dm. Well, we need to figure out what that is. Okay, so what do you think dm is? dm is going to be rho dA because we're still just dealing with the tiny part of the surface, so we're still going to be a dA. So what do you think dA is? So dA, you might think, from first go, part of the area is 2 pi r because it still has that circumference like in that last question we were looking at. But then what is the thickness of the hoop? Well, we can't say the thickness of the hoop is just dx because this is on the surface of a sphere. The thickness of the hoop is r d theta. Why is the thickness of the hoop r d theta? Well, that comes from arc length. And I should point out we're only going to be working in radians. So if you're working in arc length, the thickness of the sphere, because it's right here, that's the edge of the hoop, arc length is r theta. So if you're looking at an infinitesimal loop, the thickness is r d theta. Okay, let me know how you feel about doing all these infinitesimal areas. Kind of interesting to think about. So I want you to write down what dm is now. Because we know rho, we know dA. Go ahead and figure that out. Okay, so dm, okay, well this can simplify some. So we end up with m little r d theta over 2 capital R. Okay, now our current problem is that we have little r and theta. Little r changes as we change between hoops. Theta changes as we change between hoops. Theta is this angle right here. If I blow up this triangle, because this picture is way too crowded, we have theta and little r and big R. Let's copy some of this over to the next page. Okay, so we have this triangle over here. We want little r written in terms of r and theta. Remember, r is the radius of each individual little hoop we're dealing with. Capital R is the radius of the whole sphere. Theta is the angle that, theta is this angle right here in the picture. So that's the polar angle if you were in spherical coordinates. Okay, how do you do that? Okay, well I know that the sine of theta equals r, little r over big R. So that means that little r equals big R times sine theta. Okay, now I can reduce it so that little r is written in terms of r and theta, and dm it will only be written in terms of theta. So you might be asking, why is it that we're getting rid of little r instead of getting rid of theta? Well, I just find it easier to think about. Theta is going to run in an entire sphere. Theta runs from theta equals 0 to theta equals pi, so that'll cover the whole surface of your sphere. Whereas little r is going to start out at 0, eventually max out at r, and come back down to 0, and it's changing in a much more complicated way than theta is. So just thinking in terms of theta is actually a lot easier. So if we simplify this, now our r's cancel out, and now our dm equals, now we need to put this back in our original integral for what the moment of inertia is. Well here's an interesting point. This little r is this one. So that's actually r squared sine squared theta. And dm, so if we simplify this, we get, and to cover the whole surface of our sphere, theta needs to run from 0 to pi. Which if you're used to working in spherical coordinates, that much will make sense. But we can't fully work in spherical coordinates because rotational motion fits better in cylindrical coordinates. Okay, now we have an integral we need to do. I'll copy it over on the next page. Okay, so what I want you to do is solve this integral. Some of you may already know how to do this integral. There's a way using trig identities that's not too bad. But I'm going to give you the relevant result from the integral table if that is your preferred method. Okay, so go ahead and work out this integral. Okay, so to use the integral table, x goes to theta, and a equals 1. So we get, okay, if we plug this in, then we have, well, the cosine of pi is minus 1, so this becomes positive 3/4, and the cosine of 3 pi is minus 1, so this becomes minus 1/12. Cosine of 0 is 1. Alright, and if you work out all your fractions, you get, alright, this is what you'll find in your table of moments of inertia. So it is a bit of a mess to work all this out. In your book, they have some other method of finding this, which looks very clever. And then they say, the student should verify this by direct integration. Well, okay, we just did that together. Okay, and I really do want to hear from you what you prioritize as important when it comes to talking about rotational motion. All right, see you next week.